Hello everybody. In this video I'm going to explain what the first derivative test is, and then we're going to go over some problems involving how to find the local maximum and minimum values on an open interval AB while using the first derivative test. In the next video I will do these exact same problems, except I'm going to be doing the second derivative test, and of course I'll be explaining that in the next video, but this video is purely focused on the first derivative test and how to find these max and min local values. So, what is the purpose of the first derivative test? Well, it just helps us determine whether a critical point is a local max, local min, or it's neither. The exact definition, pulled from Cengag's textbook, is suppose that C is the critical number of a continuous function f. So these are the three things that will occur. If f prime changes from positive to negative at C, then f has a local max at C. The second thing that might occur, if f prime changes from negative to positive at C, then f has a local min at C. And lastly, C, if f prime does not change sign at C, then f has no local max or min at C. So what is this even talking about? Simply put, you're going to have a graph. And on your graph, it might look something like this. This is just an example. And you're going to have critical points here and here, right? And again, your graph is always continuous, right? So at these critical points, we notice that we are going and we are increasing over here. We're increasing, we're increasing, we're increasing. So on this side, we're increasing. After we passed our critical point, we start decreasing and decreasing. We are going negatively down. Our slope is negative. And then when we hit this other critical point, we begin to increase once more. So therefore, if we were to create an asymptote almost along these critical points, we notice a change. It goes from positive to negative to positive. That's all this first derivative test is helping us do. That's what these definitions state. So it says if f prime changes from positive to negative at C, then f has a local max at C. And this guy right here does that. It goes from positive to negative at C. So this is a local max. This next time, it goes down, 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 then up, and it's saying at B, if f prime changes from negative to positive at C, then f has a local min. And would you look at that? This guy really is our local min. That's all it's helping us do. If we don't have a graph, it's not going to be a lot harder to identify. This is like really easy and obvious because it's right in front of us. However, algebraically speaking, this definition and this test is going to be super useful when we don't want to graph it or we can't graph it. It's just too difficult. Let's just jump into our example problems and we can use this and it'll be more clear as to how useful it is. So what is even the first step? Find the local maximum and minimum values on the given for the given function. F of x equals x to the third power minus 6x to the second power plus 9x on 0 to 5. So this is an open interval. I'm going to include some example problems where we are given an interval and sometimes we're not given an interval, and I'm going to show you how to go about those problems. But for now, let's focus on the given one. So what is even our first step? Our first step is to find our critical point, similar to how we did it in the last video where we were working with closed intervals. So let's find our critical points. To do that, we must first get the derivative of our function. The derivative of our function is 3x to the second power minus 12x plus 9. Now we must set our derivative equal to 0 and factor. Our greatest common factor is going to be 3. When we pull out the 3, we are left with x squared minus 4x plus 3. Then we're going to factor once more. Okay, so we need to figure out the factors of 3 And there's really only one option, 1 times 3. So when added or subtracted, 1 times 3, right? Those two values, which one is going to give us this -4? Well, a -1 and a -3 when multiplied gives us a +3. And when added or subtracted to each other, we get a -4. So this is going to work perfectly. So inside here, we're going to put a -3 and a -1. Let's clean this up. All right, now we're just going to set these guys equal to 0. So x minus 3 equals 0, x minus 1 equals 0. We find that x equals 3 and x equals 1. So our critical points are 3 and 1. We must check to see if it falls into the interval that we're given, and it does. So we are all good to keep going. So what is our next step? Okay, that was a lot. What I like to do is I like to draw a number line. And I'll plot my critical points. So I have a 1 and I have a 3. These numbers are really important. These are critical values, right? So just like earlier, at these critical points, I'm going to draw like an asymptote like lines to separate. Okay, now we have to figure out what is the sign in between each of these, because the signs in between these 3 places is going to tell us if it's increasing, decreasing, and that will tell us if the critical point is going to be a max or a min. As a, I guess, a way to just know, I like to refer to this. I'm not even quite sure what you would call it, but this is a for sure thing to help me know what it's going to be. Without a definition, a simple picture. I hate definitions, I love pictures. So we have our C's, and then we're gonna pick a point on the left side and on the right side of our critical value so that we can see what it spits out. So if on the left we have a negative and on the right we have a positive, then that is a min, a local min or a relative min. If it's going from positive to negative, then we have a local max or relative max. So let's use this in an application. Let's pick a number on the left side and on the right side of 1, and then on the left side of 3 and on the right side of 3. The best thing to do for the middle of this is going to be picking 2, right? And for the right side of 3, we can pick 4, but then we have a problem. We can't pick 0 to go on the left side of 1 because 0 is not inclusive in our interval. So we're gonna have to go with 1.5, which is gonna be kind of annoying, but it's fine. And now, something I like to remind myself is, this is called the first derivative test. So therefore, we're going to plug in the 3 numbers that we just chose into our first derivative. Not our function, but our first derivative. So let's do that over here. F prime, and all we're doing is we're plugging in the 3 numbers that we chose, not our critical points. And we're going to plug it into our derivative. So 3 times 1/2 squared minus 12 times 1/2 plus 9. This is going to spit out, it's going to spit out a fraction, but so that we can see it alongside the other whole numbers, I'm going to write it as a decimal. So when you plug this into a calculator, it's going to spit out 3.75. But honestly, we really don't even care about the value. We just care to see if it's positive or negative. And this is clearly going to be positive. So where we have that 1/2, we know that here it's going to be positive. So now we just have 2 more things to do, and then we can now know what our local min and max are. So let's keep going. We have f prime of 2 equals, so 3 times 2 squared minus 12 times 2 plus 9, and this is going to spit out a negative 3. So this is negative, so in the middle we're going to put a negative symbol. And then we have f prime of 4 equals 3 times 4 squared minus 12 times 4 plus 9, and that is going to spit out a positive 9. Okay, so let's take a look at this little chart we have here. And if we look back to what I drew earlier, it's the same thing. We're doing the same thing we literally just did earlier, except we don't have like the function written down. So we're just trying to figure it out without having the function graphed. So let's look at the little chart I made to the top right. If it's going from positive to negative, that means the critical point is a max. So that means 1 is our max, our local max. If it's going from negative to positive, that means it's a local min. So 3 is a local min. So if you were asked, just find the local min and max, that would be it. However, most of the time they're going to ask you for a coordinate. So I'm going to show you now how to find the ordered pair for this. And that's literally just plugging in 1 and 3 into your original function and then seeing what it spits out, and that's what it's going to be for your y. So to do that, I'm going to clear some of this up. I'm going to do it right here. Let's do from blue. So all we're doing is plugging it into our original function. 1 to the third power minus 6 times 1 to the second power plus 9 times 1. This is going to give us 4. Therefore, our ordered pair is going to be 1, 4. 1 and 4. This is our local max. That would be your answer. If they're asking for an ordered pair for your local max, that would be it. Then for our local min, we would plug in 3 to our original. We get 3 to the third power minus 6 times 3 to the second power plus 9 times 3. Wow, this is ugly. Let's fix her. Okay. And this is going to spit out 0. If we're to plug that in, it'd spit out a fat 0. Therefore, ordered pair is going to be 3, 0. And this is our local min. So these are honestly really easy. These are pretty easy. We do have some good examples coming up. The next one's pretty easy too, but the next two after that, these are big boys. Okay, so let's do this next one. This one we're not given an open interval, so we have to use our just knowledge, basic knowledge. We're given a polynomial. She's big, she's chunk, and most chances are the domain's gonna be all real numbers, and for this one, it is all real numbers. So we don't have to worry about anything. We're gonna be just fine. We can just jump right into it. So we're going to just find the derivative, 3x squared minus 6x to the first minus 9. Set her equal to 0. Then we're going to pull out our greatest common factor. Our greatest common factor is going to be 3. Then we're going to factor her. We're going to get x minus 3 and x plus 1. Because again, if you were to look at this guy and list out the factors, you would get basically just 1 and 3. And when you look at these numbers, when added or subtracted, when does it give you -2? Well, it gives you -2 when you do this, right? Therefore, we're going to put in a -3 and a +1 in here. Let's set this equal to 0. x minus 3 equals 0, x plus 1 equals 0, x equals 3, x equals negative 1. So our critical points are 3 and negative 1. Now our next step is going to be finding a value after the 3, before the 3, after the negative 1, and before the negative 1. Let's make our number line. We're going to have a negative 1. We're going to have a 3. Okay. Again, we're not given an interval, so it doesn't really matter. We're good. Let's pick a number. I'm going to pick 0. That's always like the easiest way to go about it. Then I'm going to pick the obvious choice over... Oh, okay. Then I'm going to pick the obvious choice over here, which is going to be negative 2. And then the obvious choice over here would be just 4. Getting as close as possible would be nice. Now we must figure out what these signs are, because that's going to tell us if negative 1 is a max or a min, and if 3 is a max or a min, right? Okay. Now we're going to plug these 3 values into our derivative, right? Our first derivative, because it's called the first derivative test. Very good. Let's do this here. F prime of, let's do negative 2 first, equals, and our derivative was 3x squared. So 3 times negative 2 squared minus 6 times negative 2 minus 9. This is going to give us f prime of negative 2 spits out a 15, which is positive. So we know she is positive over here. Now let's do our next one. F prime of 0 equals 3 times 0 squared minus 6 times 0 minus 9. So f prime of 0 is going to spit out that negative 9. So we get negative. Okay, oh my gosh, f prime of 0. Not even of 0. Hello? Okay, 4 equals 3 times 4 squared minus 6 times 4 minus 9. And f prime of 4 spits out 15, which is positive. So we have our positive. And if we remember our definition, or again, my little picture, I like my picture way better than the definition any day. So I'm going to draw my little picture because she's going to hit every time. Okay. All right. And all my little picture says is negative and positive. Then that's min. Positive, then negative, then that is your max. Therefore, negative 1 is our max, and 3 is our min. To find the ordered pair, we're going to have to plug in our critical points into our original function. So I'm going to clear this bottom portion out. And now let's do that. We get f of negative 1 equals negative 1 to the third power minus 3 times negative 1 squared minus 9 times negative 1 plus 16. When we plug this into a calculator, we get 21. Therefore, wow, that is an ugly arrow. We get negative 1 comma 21 is our max. for our other critical point, which is 3, we get 3 to the third power minus 3 times 3 squared minus 9 times 3 plus 16. This is going to spit out a negative 11. Therefore, our coordinate is going to be 3 comma negative 11 is our min. And that is all for this problem. Okay, going back to when that gives us an interval. So we're given an open interval. We have f of x equals x squared plus 1 over x. Again, we're going to take the derivative. But before we take the derivative, I'm going to simplify her. Also, be sure to consider, even if they give you an interval, be sure to consider your domain. So our domain for this one, it cannot equal x. It can be anything but 0, because when it's 0 in the denominator, we have it as undefined, right? So it can't be 0 at all, period. So I just want to make that note. Now let's just jump into it. I'm going to simplify her before I take the derivative. And this is totally legal. We can do this because that's the equivalent as what it was before. I'm going to simplify her, and I'm going to put this girl into proper form because she's not in proper form, so that we can pull the derivative. So we get f(x) equals x plus, and again, putting her in proper form, which means we get x to the negative 1 power. Now we can take the derivative. So f prime of x equals 1 plus negative 1x to the negative 1 minus 1. And I'm going to show all the little steps for this because maybe you've never seen this before. So when this is simplified, it's negative x to the negative 2nd power. Now, this is technically in bad form, so I'm going to put the negative exponent in the denominator so that it's positive now that we're done pulling the derivative from it, and then I'm going to equal it to 0. So f prime of x equals 1 minus 1 over x squared. We can now equal her to 0. This is kind of a trip. Then just solve like normal for our x values. Negative 1, or minus 1 rather. Negative 1 equals negative 1 over x squared. Then you can do a number of things. I always like to cross multiply if I can. So remember, under every single whole number, there's a 1. We just don't write it. So I'm going to be cross multiplying. I'm going to multiply these two and then these two. Okay. So when I do that, I'm going to put her over here because we're kind of running out of space. Negative 1 times x. Actually, I could throw her wherever I want. So I'm going to do negative 1 times negative x squared. That's going to give me x squared, a positive x squared, equals 1 times 1 is 1. Then we can just do the square root to get rid of the 2, because remember, in every little square root, there's always a 2. It's just not written, it's implied. So that's going to take care of this 2. Then we get x equals plus or minus the square root of 1, and the square root of 1 is 1. So let's see, we have x equals negative 1 and x equals 1 as our critical points. However, our interval states that it's from 0 to infinity. Therefore, this girl is not a critical point for the given interval. We only have one critical point for this function. So this is going to be a little bit easier when finding if it's a min or a max, because now we can only just deal with 2 numbers instead of 3, right? Okay, now that we've found x equals 1, I am going to clean this up because I have no room. So let's clean her up. Cut. Okay. Let's make our number line. Our critical value is 1. Now we must pick 2 points on the left and on the right of her, and we cannot pick 0, so we're gonna have to go with 1/2, and we can certainly pick 2 because it goes to infinity, right? Now we must figure out what are these signs gonna be. So let's plug in our 2 chosen values into the derivative, right? And if we don't remember, I probably shouldn't have erased that. Let me write that first. Remember, our derivative was f prime of x equals 1 minus 1/x squared. That was her in her proper form. So let's plug in our 2 values for x in our derivative, and we get 1/1/2 squared. I'm going to show all the work for this one because I feel like some people might make a mistake doing this. 1 minus 1/1/4, because when you square 1, you get 1. When you square 2, you get 4. Therefore, we have 1/1/4. This, illegal. We cannot have that. So we need to put her in a proper form. To do that, we can just do the reciprocal, which is 4/1, so that this cancels out. Then we get f prime of 1/2 equals 1 minus 4. 1 minus 4 is f prime of 1/2 equals -3. So it spit out a negative. So over here, we have a negative. Now, let's find out what our 2 is going to give us. F prime of 2 equals 1 minus 1/2 squared. This one's much easier, much cleaner, right? We get 1 minus 1/4. We cannot combine these until they have the same denominator. Therefore, we need to multiply the 1 by 4/4. We get f prime of 2 equals 4/4 minus 1/4. This gives us, hello? Wow. Okay, f prime of 2 equals 3/4. And this is a positive value. Over here, we get a positive value. If we look back at my little test, we are going from negative to positive. Therefore, our critical point here is a min, our local min, or relative min. If we are to provide a coordinate, we must plug 1 into our original function. So I'm going to clean this up down here so that we can do that. Okay, we have f of 1 equals 1 squared plus 1/1. This is just going to give us 2/1, which is just 2. Our ordered pair is 1, 2. And this is a local minimum. That is our answer for example 3. Wasn't so bad. It was a lot. Ironically, it was a lot considering we just had to plug in 2 numbers. Last one. This requires us using the quotient rule. It's honestly not going to be as bad as the last one, ironically enough. This one does not have an interval either, so we do not have to worry about it, unlike the last one. So let's do this now. It's going to be, there's like a thing. What do they do? It's like high D low or low D high or something. I can't sing that tune. I just can't. Like in my brain, I just see it. We're going to have g of x times f prime of x minus g prime of x times f of x over g of x squared, where g of x is our denominator and f of x is our numerator. Let's do that now. F prime of x equals x squared plus 1 times the derivative of the top, which is 2x, minus the derivative of the bottom, which is ironically 2x, times the top, which is x squared, all over our denominator squared. Now let's combine our like terms. We get f prime of x equals 2x to the third power plus 2x minus 2x to the third power over x squared plus 1 to the second power. Now, again, we can still combine our like terms because we have this girl and this girl. Let's combine those, and then we can set this thing equal to 0. So these cancel out, and we're left with 2x over x squared plus 1 completely squared. Again, to find our critical points, we do not set the denominator and the numerator equal to 0. If we were to do that, then the whole derivative would become undefined and we wouldn't get anything. Therefore, we only take the numerator, 2x, and we equal her to 0. When we divide by 2 on each side, we get x equals 0. Therefore, our critical point, and our only critical point for this function, is just going to be 0. Now I'm going to clean this all up because we don't really have space. Except this time I'm going to make sure that I keep the derivative up there because that's pretty important. All right, so our critical point is up here and our derivative is right there. Let's make our number line. And let's write our critical point, which is 0. Now we must select a point on the left and on the right. We don't have intervals, so we could just pick whatever we want. I'm going to go with -1 and 1. Let's find out what these signs are going to be. We do this by plugging into the first derivative, right? Because it's the first derivative test. And we're going to get 2 times -1 over -1 squared plus 1 all squared. This is going to spit out a -1 over 2. So we get a negative. On the left, it's going to be a negative symbol. Let's plug in 1 into our derivative. We're going to get 2 times 1 over 1 squared plus 1 all squared. This is going to spit out a positive 1/2. On the right, we're going to have a positive. Okay, so based off of my little picture, it goes from negative to positive. That means it's min. And this guy certainly goes from negative to positive. Therefore, 0 is a local min. To find our coordinate, we must plug in 0 to our original function. I'm going to clean this up so we can do that. Okay, this is going to be really easy. F of 0 equals 0 squared. Okay, Siri needs to mind her business. She's acting a little too crazy. 0 squared plus 1. We get f of 0 equals 0 over 1, which is basically just 0, right? Therefore, our coordinate is going to be 0, 0, and that is our local min point. That is all for this video. In this next video coming up, I'm going to be doing all of these problems, but using the second derivative test. So if that's something that is interesting to you, be sure to check out that video. And thank you so much for watching. Bye.